Hi there. I'm going to be working out some of the questions and problems from our linear motion packet. I'm going to be giving you guys the key, and I thought that I would work through some of the ones that we either had not had time to talk about much in class or that we did talk about, but maybe I didn't work them out for you in class. The first thing I want to do is the graph that's on page 2. It is our position time graph. You'll see that I've given you some sample graphs that tell you what they mean. In other words, if they have a positive slope, meaning if they start towards the origin, 0, 0, and move up, the position is increasing over time, that would be a positive velocity, or something that's moving in the forward direction. If they have a curvy line, or a changing slope, that would be something that is experiencing a change in velocity or acceleration. And if they have a descending line where the position is larger and over time it gets smaller, that would mean a negative slope or a negative velocity, something that's moving backwards or left, as this thing states. So on the graph at the bottom, I have an object that's moving through space, and we have some questions about it. The first question, what is the object doing at A? So during segment A, the line is straight. If we wanted to, we could calculate the slope of that line using the change in the y-axis over the change in the x-axis. And that line is straight, so that means that the slope is constant, and it has a positive slope. So at position A, or during segment A, the object has a constant positive velocity. During B, we notice the line becomes horizontal or flat. The slope of a horizontal line is 0 because there's no change in the y-axis. It started at 60 meters and it finished at 60 meters. So that means it was sitting at the 60-meter position during the entire time period from 10 to 30 seconds. That means that the object is not moving. What is the object doing during C? Well, now we see the line is going back towards the origin where it started. It was at 60 and now it's back at 40. If we found the slope of this line, we would see that it is negative, and so that means that the object, because it's a straight line, it has a constant velocity, but it's a negative velocity. You could also tell me that in addition to this information, you could tell me that during A, the object is moving to the right, and during B, the object is moving to the left. That would also be acceptable. What is the object doing at D? Well, D looks kind of like A, doesn't it? It's a straight line, so we know the velocity is constant, the slope is constant, and it's also getting farther away from the origin. If we took the slope, we would find it to be a positive number, so it's going to be the same as A, a constant positive velocity. The last question is the object's velocity greater at A or D? For this one, you just have to compare the slopes of the lines, and you could hold up a ruler if you wanted to see which line is steeper. But if you do the math for A, that would be 60 minus 0, because it ends, the initial is at 0. So the change in y, or the rise, would be 60 minus 0. And then the run, or the change in x, would be 10. So that is a velocity of 6 meters per second. During segment D, our initial position is 40 and our final position is 100. So we would say 100 minus 40, and we would divide that by the time period. It started at about 45 seconds to me. That's what it looks like. And it went until 60 seconds. So you would take the change in the time. That would be 60 over 15, which is, I believe, 4. I had to check it and make sure. So the answer then would be A, because 6 meters per second is greater than 4 meters per second. Now I've moved on to page 3. We're going to work some of the velocity, distance, time equations. We worked these in class. We know that we're going to use this equation here, d equals vt. In addition to that equation, we can also utilize the triangle that we talked about in the last video. The triangle can help if you're a little nervous about the algebra. This can be helpful to make sure that you're dividing the right thing by the right thing. So the first question, a football is thrown north 25 meters in 2.2 seconds. What is the velocity of the ball? So we have a distance of 25 meters and we have a time of 2.2 seconds. And we are looking to find the velocity of the ball. Now they did tell us that this was thrown north, so let's remember that we have that information to include for our velocity. We have d, t, and v. Obviously this is not an acceleration problem because we're not talking about acceleration. There's only one velocity given to us, so that's how we'll know we use this question. On the packet, it's all divided up. All the questions that use this equation are together. On the test, they're going to be mixed up, and you'll have to identify when to use this equation and when to use one of the kinematics equations. If we're looking for v and we want to use our triangle, we can cover the v up and see that we're going to do d divided by t. So I'm going to write that as my equation. And then I'm going to plug my numbers in. V equals 25 over 2.2 seconds. And I'll find the answer is 11.4 meters per second. And then if you write the answer over in the final spot, you can go ahead and include the distance with it. Not the distance, excuse me, the direction. That would be 11.4 meters per second north. Because velocity is a vector, if you're given some kind of direction information, you'll want to include that as part of your velocity answer for 11.4 meters per second north. In our next question, we have a cyclist who travels 2.3 hours. At a velocity of 15 kilometers per hour. So it tells us that's velocity, but you can also tell by the unit. How far did she go? How far? That question is asking for distance. So again, we're going to use our equation that has v's, d's, and t's in it, but we just need to rearrange it a little bit. Since we're looking for distance, we're going to use it the way it's written. This is the equation that I'll give you on the test, so you'll be able to use it just like this. D equals vt. And so when we plug our numbers in, 15 times 2.3, we will get an answer of 34.5. And the units for this one, you just need to be careful when you're doing distance and look at what you've been given to work with. Because the velocity that we had was kilometers per hour, that means that our distance is going to be in kilometers. The next question, C, how long does it take for a car moving 62 kilometers per hour to go 3.1 kilometers? So the first number we give, it doesn't label it, it just says moving 62 kilometers per hour, but because we've studied and know our units, we know that kilometers per hour is the unit for velocity. 3.1 kilometers, that's the unit for distance. And we want to know how long does it take. So that's asking us to find time. So again, just one velocity, no talk of acceleration. So we're going to stick with our dVt equation. If we're looking for time, you can either rearrange this equation that you'll be given to solve for t, or you can use the triangle, and you can cover the t up. That's what we're looking for. When we cover it up, we see that it's distance divided by velocity. So I will write that down here for my equation. And now I will plug the numbers in. So if we take 3.1 kilometers and we divide it by 62 kilometers per hour, we get 0.05 hours. That's kind of a weird measurement of time. If you want to put that in something more recognizable, you could multiply it by minutes, because there's 60 minutes in an hour. So I would accept either answer, 0.05 hours or 3 minutes. 3 minutes is what you get if you take 0.05 times 60. These next problems are show that problems. I noticed on my Google document that I did not give an explanation for what show that problems were. So if you did not print this offline, or if you did print this offline, you might not understand why this question reads the way it does. Show that problems give you some information to calculate with, but then they also give you the answer. So it's a little hard to get used to that. Some students look at the problem and they say, I don't understand what I'm solving for, because they gave me everything I need. They gave me distance and time and speed or velocity. But a show that problem is asking you to show how you arrive at this answer. So you should take the two given pieces of information and then show me how you would calculate that. It's like a proof in math. So these I don't have a fancy table for, but we're going to continue to use the same method that we've been using, so that I just wanted you to get used to how to piece together all your information. Sometimes it helps to have a table that's asking for certain things to remind you of the steps that you need to go through to get to the answer. In this question, a ball rolls down a 3-meter incline, so the distance is 3 meters. And it takes 1.5 seconds. That is a time. And it says show that the average speed is 2 meters per second. So I'm going to calculate the speed on my own. Now I'm going to call speed velocity, because we can do that for right now for our calculation purposes, since our equation has a v in it. We are looking for velocity, and if we use our equation or our triangle, we will find out that velocity is equal to distance over time. We used the same technique up here in the first one when we were looking for velocity. So we'll take our distance of 3 meters, we will divide by 1.5 seconds, and we'll get 2 meters per second. So we just showed that when these are true, this is true. The answer is correct, 2 meters per second. Oh, let me see. I'm going to stop this and move my camera a little. Okay, the last two questions for velocity, distance, and time. This is number 6E, and it's on the 4th page. A grizzly bear has a top running speed of 13 meters per second, so that is a speed or velocity. Two campsites are 65 meters apart. 65 meters is a distance. Show that it will take him 5 seconds to run from one campsite to the other. So we are trying to prove how long it's going to take him to get from one campsite to the other. Since we are looking for time, if we refer to our triangle over here, if you cover the t up, we'll take the distance divided by velocity to find our time. The answer to this question is 5 seconds. So you've only got 5 seconds to run from the bear and jump in your tent. Our last VDT equation is about a train. A train has an average velocity of 17 meters per second for an hour. Show that it covers a distance of 61,200. Now, if you look at this question, there's only two numbers. There's this number, and then they already have us show that with this number. There's a hidden number in here in the words, and we talked about this in class. It happens from time to time. The hidden number is for an hour. That is the time. And we can't use hours. Okay, my last video got interrupted, so I'm going to pick up where I left off. We had the train with an average velocity of 17 meters per second, so that's V. And then the distance, it said for an hour. Now that's the time, it's 1 hour. It has it in words, so sometimes you have to read the words to find the numbers that you're looking for. We have seconds and then we have hours. Those units do not match each other. So what we need to do is write the time in hours. We have to change that to seconds. So we're going to take 1 hour and we're going to multiply it by 60 minutes. And we're going to multiply that by 60 seconds because in every hour there are 60 minutes and 60 seconds in each of those 60 minutes. So that ends up equaling 3,600 seconds. And we're trying to prove that the distance that's covered is 61,200 meters. So we're looking for distance, and that's going to be our simplest V times T equation. So we'll take our velocity and we'll multiply by 3,600. We will come up with a distance of 61,200 meters. The remainder of the problems on this in this packet have to do with acceleration, and for that reason we're going to have to use an equation that has an A in it. These are the three major kinematics equations, and on the right hand side I've told you what is interesting about each one. There are three, not because we want to torture you, but because each equation is missing some information which makes it useful. If you're not given the distance, then you want to use the first equation because there's no D in that equation. If they don't give you any velocity that's final and they only have initial velocity, then this second equation is the best one to use. And if the equation or the problem has no time given, then you want to use the last one because this is the only equation that does not have a T in it. The algebra is more complicated with these, and unfortunately we cannot use a simple triangle to help us solve these problems. But as I mentioned in class, on each problem on the test, you will be given 1 point if you correctly identify all the given information, if you can label the numbers in the problem. You will be given 1 point if you identify which equation to use and you pick the right one. You will be given 1 point if you solve the numbers and get the right answer, the right number answer. And your 4th point will be from the unit if you remember to put the right unit on the answer. So you have the opportunity to get 3 out of 4 points on every math question on the test, even if you can't actually plug the numbers in and algebraically solve for the final answer. So if the number doesn't come out right, it's okay. I just want to be sure you can identify what you're given, pick the right equation, and that you understand what you're looking for, what your final unit's going to be. So we worked through these in class. I'm going to go ahead and work them again just because sometimes in class you're not having a good day and maybe you weren't paying good attention. Maybe you regretted not writing everything down that I said. So I'm going to go ahead and jot down the answers to these as well as the remainder that we did not work together. A bus is initially traveling at a speed of 70 kilometers per hour. So the kilometers per hour tells us that's going to be a V. I know it says speed because I wrote the problem, but it's okay for you to call that velocity. It accelerates at the rate of 2.5 kilometers per hour squared. So that is our acceleration, in the kilometer per hour squared unit also tells us that that is acceleration. And it does so for 43.5 kilometers. So that is distance. What is the final velocity of the car? So we are looking for VF. Now in these problems, since there's acceleration, we are going to need to differentiate between initial and final velocity. It tells us at the beginning that the bus is initially traveling at this speed. So we're going to need to add a little VI by the 70, and then we're looking for the VF. Now all you have to do, and I know that makes it sound very simplified, but really, once you do this part, this is the hard part, and now you can look and find an equation that has these 4 items in it. We need VI, VF, A, and D. And if you look through your list, you'll find that the last equation is the one that fits the bill. We don't have a time to work with, so we're going to use the equation that does not have time in it. Now we're going to plug those numbers in. And you can simplify the 70 squared, and you can simplify this section, and you can add them together. And when you do that, you'll get a rather large number. Sometimes it's easy to forget to square that VF, or sorry, square root the VF before we finish our solution. But just remember, a bus doesn't usually go 5,000 kilometers per hour. That's too big. So we're going to take that radical, put it over each side, and we'll end up square rooting the 5,000 number to find that the velocity is 71.5 kilometers per hour. And I hear my youngest child home from school, so I'm going to pause it and go fix him a snack. All right, back to number 7B. A race car initially at rest, accelerates uniformly at 10 meters per second squared for a distance of 100 meters. How long did the race car accelerate? So it says the race car initially at rest. There is a variable that's hiding in some words. If something is initially at rest, that means its initial velocity is equal to 0. It accelerates uniformly at 10 meters per second squared. That's the acceleration. For a distance of 100 meters. How long did the race car accelerate? The how long question in this case is going to be time. How much time did it take it to reach 100 meters if it was accelerating at that rate? We have a VI, an A, a D, and a T. So if we look back at our equations to choose from, the equation that best fits what we've got and can do it in one step is the second equation. There's no final velocity in this equation, and we don't have a final velocity to work with in our givens. Now we can plug the numbers in that we have to work with. Our distance is 100. Our initial velocity is 0. So this term, VIT, is just going to go away completely. We won't even have to worry about that. Now we can simplify. I'm going to multiply 1/2 times 10 to combine these two numbers, and I'll get 5. Now to get the t by itself, or the t squared by itself, I'm going to divide both sides by 5. Oops. So t squared is equal to 20, and then since we've just got a squared here, all we need to do is take the square root of both sides, and we'll find out our answer is 4.5 seconds. Our next question, C, a boat can be accelerated from 0 meters per second to 6.5 meters per second in 9.2 seconds. What is its acceleration? We have the word accelerated that's right in front of these two numbers, but these numbers have variables of meters per second, and that's a velocity variable. It's telling us the boat can be accelerated, but these numbers that it's given us are velocities. The 0 is our initial velocity, and the 6.5 is the final velocity. 9.2 seconds is the time. And the question's asking, what is the acceleration? The equation that we're going to use for this one is the one that does not have distance in it, because we have a VF, a VI, an A, and a T to work with. This is everybody's favorite equation because it's the simplest one. So now we'll plug our numbers in. To get the A by itself, we'll divide both sides by 9.2. Our A is going to equal 0.71. And that will be meters per second squared because it's an acceleration. In D, we have a ball that undergoes uniform acceleration of 2.5 meters per second squared. And then in parentheses it says beginning at rest. That means we have a number that's hiding in these words. That would be our initial velocity, and that would equal 0. What is the velocity of the ball 4 seconds later? So they're looking for a velocity. We've already found the initial velocity, so we're going to look for the final velocity, but they gave us a time of 4 seconds. To me, it looks like we have the exact same variables to work with that we did in the previous question. 2 V's, an A, and a T. So we're going to use the same equation. And I don't even think I need a calculator for this one. Meters per second. It takes 6.4 seconds to stop after the driver starts braking at a velocity of 32 meters per second. The deceleration is at a rate of -5 meters per second squared. How far will the car travel before it stops? The first number we're given is time. And then it says it takes that long to stop after the driver starts braking at a velocity of 32 meters per second. Now that's kind of a complex sentence, but there's actually 2 velocities given to us in this sentence. They mention that the car comes to a stop after they apply the brakes, going that speed. So the initial velocity is 32, and the final velocity is 0. We're given the acceleration of -5. And they want to know the distance. We have a lot of variables to use. In fact, we have all the variables to use. T, both of the V's, the A, and the D. Since we're finding distance, we're going to not want to use this equation because there's no D in this equation. We definitely want to choose an equation that has a D in it. And the equation that looks the best to me is this middle equation. Although it really doesn't matter, you can use either of those equations and you'll come out okay. So if you did it using the VF squared equation, that's fine. Let's see if your answer matches my answer. Sometimes there's two ways to go about the same problem. Now you'll notice the -5 in there. I gave you the -5, but you want to be sure that you keep it negative because it's going to make a difference. This term here is going to be positive. And this term over here, if you do 1/2 times -5 times 6.4 squared, by the way, only square the 6.4, don't square this whole thing multiplied together. You're going to get -102.4. So our distance will end up being 102.4. If you did the same, got the same answer using a different equation, congratulations, because that should have worked out well for you. In F, we have what acceleration is required to take a boat from 13 meters per second to 26 meters per second over a distance of 1250 meters. So they're asking for acceleration, and then we're given 2 meters per second, 13 to 26. Those are our two velocities. Initial is 13 and final is 26. We're given a distance and we're looking for the acceleration. We've got two V's, an A, and a D. So we're going to use the equation that doesn't have time in it because they did not give us a time to work with. So now we've got 676 equals 169 plus 2500A. These are sometimes confusing to do with the algebra. We need the A by itself, but we first have to get rid of this term. We don't want to accidentally add 169 to 2500A because this term does not have an A on it. This term does have an A on it. So these are different, and we have to take this one and subtract it from both sides to combine it with a number that's on this side. So 676 minus 169 is 507. And now we can reach the point where we can go ahead and get the A by itself. We'll divide both sides by 2500 and we'll find that our A is equal to 0.2. G, an F-14 Tomcat fighter jet, goes from rest to a speed of 75 meters per second in 2.5 seconds. Show that the acceleration it undergoes is 30 meters per second squared. The jet goes from rest to a speed of 75 meters per second. Those are both of our velocities. Our initial velocity is 0. Our final velocity is 75. And our time is 2.5 seconds. question wants us to show that the acceleration is 30. So we're looking for A. We have both V's, a T and an A, so we're going to use this equation. And now you should be getting the hang of it. We're going to divide both sides by 2.5 to get our A all by itself. And 75 divided by 2.5 is 30. So we proved that that is the right answer. Zed is on rollerblades on a hill. He starts from rest and skates for 5.5 seconds, accelerating uniformly at 3.5 meters per second squared. Show that the distance he traveled is 53 meters. He starts from rest. That's a word, but it gives us a number, doesn't it? Our initial velocity is 0. He skates for 5.5 seconds. So we have a time. Accelerating uniformly at 3.5 meters per second squared. That's our acceleration. We want to show that the distance he traveled is 53. So we're going to be looking for distance. We have VI, T, and A. We're looking for D. So we will be using our D equals VIT plus 1/2 AT squared. The VIT will be 0 because our initial velocity is 0. When we simplify this term, we want to be sure to only square the 5.5. We don't want to square 1/2 times 3.5 times 5.5 and then do the square, or we'll get the wrong answer. You'll find the answer here does happen to be 53 meters. The last one of these, a cheetah accelerates from rest to a velocity of 23 meters per second with an acceleration of 6.5 meters per second squared. So he accelerates from rest to 23 meters per second. Those are both of our velocities, initial and final. All right, my camera cut off, so let me pick up where I left off. We have an initial velocity of 0 and a final velocity of 23 and an acceleration of 6.5 meters per second squared. We're trying to prove the distance was 41 meters. So we're looking for distance, just like we were in this previous question. Just because you're looking for the same thing doesn't mean you're going to use the same equation. In this equation, or this problem, we had a T to work with, but here we don't. We have two V's and an A, so we're going to have to choose the other equation that has D in it. So now we can plug in our numbers. $23 squared is, I'm trying to find my problem because I worked this already. There we go. 529. And that was 6.5. Kind of hard to see that. So we're going to divide both sides by 13. And when you do that, you'll find that you get 41. Let's take a look at this graph section. The last graph in the packet is a velocity time graph. In velocity time graphs, we have velocity on the y-axis and time is on the x. The previous ones we looked at had position on the y-axis. Now if you see a flat line going across, it doesn't mean that the object is not moving. It means that it's moving at a constant velocity, because whatever this number is, where the blue line is, that would be the velocity of the object. So this is a positive velocity, it's going forward, and it has a constant speed. Now if we see a line with a positive slope, we're going to be able to tell what the acceleration of the object is. In a velocity time graph, the slope of the line is going to be the change in velocity over the change in time. And that's the definition of acceleration. So this positive slope would show us that this object has a positive acceleration. It's moving forward with increasing speed. And this negative slope over here tells us that the object has a negative acceleration. We've talked about positive and negative accelerations in class, and if you look at the points on the graph, this completely lines up with what we've discussed. On this graph, the velocity is getting bigger and bigger as the time passes, and in this graph, the velocity is getting smaller and smaller as the time passes. This would be like an object rolling down a hill, and this would be an object rolling up a hill. The shape of the graph obviously doesn't have anything to do with what's happening. In our section down here, we have a graph that's got a lot of things going on, and we have questions on the side. It asks us to find the acceleration of the object from A to B. So this line, A to B, if we found the acceleration of that object, what we would want to do is analyze the change in our velocity from here to here and the change in the time. So this is going to be, oops, sorry, I was off. I'm trying to adjust my zoom. So the slope is equal to the acceleration. So that would be 10 minus 0, because we were at 10, and then initially we were at 0. And then the time period would be 5 seconds. So that is 2 meters per second squared. What is the acceleration of the object from B to C? B to C on our graph is horizontal. There's no slope. So the slope of this line is 0, and that's also the acceleration. What is the displacement of the object from E to F? Oh, I skipped one. Where is the velocity 0? So this is where it gets a little confusing, because on the previous graphs the velocity was 0 when it was horizontal. But now you just have to remember the graph is plotting velocity. So we just have to go down and find the 0 for velocity and go over and say that it's 0 from D to E. Or you could say from 13 to 16 seconds. That would also be correct. Now we can do displacement. What is the displacement of the object from E to F? For this part, I mentioned up here above that the displacement of the object being graphed is found using the area under the line. So I'm going to draw a line up here from the base to F, and I'm going to draw this over, and I'm going to sort of shade it in. Sorry, now you can see it. So this triangle that I've shaded in represents the displacement of the object. If we take this triangle and find the area of it using the numbers for our x-axis and our y-axis, we'll find the displacement. Displacement will be equal to 1/2 the base, which is from 16 to 21. That would be 5 times the height, which would be from 0 to 5. So 1/2 times 5 times 5 will be 12.5 meters. Since these numbers are the same, I'm just going to label where they came from. So the displacement again is the area of that triangle. It's everything that's underneath the line. I'm not going to give you any weird shapes on the test. You're either going to get a rectangle, which is basically the base times the height, or you're going to get a triangle, which is 1/2 base times height. The base went from 16 to 21, so that's a total of 5 seconds. The height went from 0 to 5. The last question, what is the acceleration, or when is the acceleration of the object negative? You're looking for a negative slope for that because the slope is equal to the acceleration. So that would be from C to D. It says the question is when, so you just have to look and see what time C is. That's 10 seconds. And then D is at 13 seconds. So that would be 10 to 13 seconds. On to the last page. The last page has to do with free fall. Free fall is when you take an object and you drop it and it's free to fall without air resistance and be under the influence of gravity. The only thing that makes free fall questions any harder is that you just have to be intuitive about things that you know, because they don't give you many numbers to work with in the question. I've written at the top of the page some of the givens, and I'm going to go through this kind of quick because I'll probably have time to talk about it in class. But obviously, acceleration of gravity is something that we know. It's -10 meters per second squared, and it's negative because it's directed downward. We know if we drop an object that it was had an initial velocity of 0. And we know if we throw something up in the air that it's going to come to a stop eventually at the top of the path. And so the final velocity, when we calculate then, could be 0. And that will give us information about where the top of the path is or how long it takes to get to the top. So let's work through these 5 problems and we'll be done with our packet. In A, an egg falls from its nest atop a 16-meter tall tree. How long does it take to hit the ground? The 16-meter tall tree is a distance, and that's the only number that they gave us in the question. There's not even any words in the question that we could be reading to find numbers, but we're going to refer to the top of the page to some of the things that we know. We know the acceleration of any object that's falling is -10 meters per second squared. And then we also know that since the egg fell out of the nest, its initial velocity was 0. The question is, how long does it take to hit the ground, and that's time. Now before we go on, I want to point out one thing, and it's not going to make a huge difference if you forget this, but technically this distance is -16. And that's because if you had a tree and the egg was somewhere up here in a nest in the tree, that the distance that it fell would be downward, and just like gravity, that would be 16 meters downward. So it's okay to put a negative on both of those. It's just going to cancel out when we work the question. D equals VIT plus 1/2 AT squared is the equation that we'll use because we have a D, an A, a VI, and a T. Our VIT term is going to be 0. And when we solve this, we're going to see that the negatives are going to cancel out. And let me look for my work over here. That's going to be 3.2 equals T squared. And when we square root both sides, we're going to get a time of 1.8. In the second question, a red ball is tossed upward and reaches a maximum height of 3 meters. Find the initial speed it was thrown with. If the ball was tossed upward, the height it reached, we know, is the distance. We know the acceleration of gravity is -10. And then if we remind ourselves up at the top, what other thing, you're either going to know the VI or the VF. Well, the question is asking for the initial velocity it was thrown with. So that's not going to be 0 because it was thrown upward. So we know it's not going 0 when it leaves the hand. But at the top of the path, it says right here, if it's thrown upward, the VF is equal to 0. So that's one of the things we know. There's some assumptions to make in these questions, and once you know how to make those assumptions, they become much easier. So we're looking for VI, the initial velocity. We have VF, A, and D. By this point, you should be feeling a lot more comfortable with these big, ugly equations. They shouldn't seem quite as scary as they did at first. This one sets up a little differently than what we've looked at before because we have the 0 on the other side of the equal. So now we have the variable we want and we have a number over here. We need to move this to the other side. So you can actually add 60 to both sides and you'll get 60 equals VI squared. You'll take the square root of both sides and you'll end up with a VI equal to 7.7. In C, a coin takes 8.5 seconds to fall from a high building. Find the velocity of the coin before it strikes the ground. So the coin's not being tossed up in the air, it's being dropped. And when something's being dropped, we know the initial velocity at the very top is equal to 0. They gave us the time of 8.5 seconds, and we know the acceleration is -10. So now you can see in a lot of these how many of the known things are the same. They just keep showing up over and over again. We're looking for the final velocity, VF. We have two V's, an A and a T. So our equation is going to be that nice simple equation. And I don't even need a calculator to solve that. So our answer is -85 meters per second. That just means that the velocity is downward. And boy, that's a big number, right? That would be very painful if a coin hits you in the head after it fell from a super tall building. 2 more questions to go. Will tosses a ball straight upward with a velocity of 18 meters per second. Show that it will be in the air for less than 4 seconds. So it tells us that he tosses the ball upward. It doesn't use the word initial, but what you have to tell yourself is that if he tosses it upward, that we know at the top its final velocity is going to be 0. And right down here at the bottom, that's the initial velocity. That's our 18. And of course we know acceleration is equal to -10. And we're looking for how long it's going to be in the air. That's our T. We have VF, VI, A, and T. So we're going to use our simple equation again. 0 equals 18 plus -10t. And when we solve, we're going to move this 18 over. Now to get the t by itself, we'll divide both sides by -10. Our negatives will cancel out, and we'll end up with 1.8 seconds. Now, I'm going to write, watch out, because this is the time that it takes to go up to the top. So I'm going to just make a note that it takes 1.8 seconds to reach the top. So therefore, the total time is equal to 3.6 seconds. So you have to take this time and you have to double it. That's the only disadvantage to the assumption that we made over here, that the final velocity is 0 at the top. If you make that your final velocity, what you're doing is you're solving for the time to get from Will's hand to the top of the path. And you have to remember that it's 1.8 seconds to the top and another 1.8 seconds to get back down. The coin was in the air for less than 4 seconds. It was in the air for 3.6 seconds. And the last question, Craig, he throws a water balloon straight upward to his friend in a tree 8 meters above. So our distance is 8 meters. Show that he must throw the balloon with a minimum speed of 13 meters per second. So if he's throwing the water balloon up in the air, then the water balloon is going to come to a stop right before it reaches his friend in the tree. So this is a little tricky again. I gave you 2 harder ones here at the end with the time, but we're going to assume that our final velocity is 0. And that way our friend who's in the tree can catch the water balloon without it hitting him too hard or busting. And then, of course, our acceleration is -10, and we're trying to figure out what his minimum speed to throw it with is. So that's our initial velocity. If you want to draw a picture of this, if you're confused before you start, I'll try to squeeze it in here at the bottom. There's our water balloon. We're trying to find out the initial velocity so that the balloon can go up and then just come to a stop. Our friend is going to be up here at the top to catch it. We don't need it to be going too fast past him. So that's why we set our final velocity equal to 0. So to find the speed he needs to throw with, we've got V, A, and D. That's our equation with the squares. VF squared is going to be 0. VI squared is what we're looking for. So we have 0 equals VI squared plus -160. And we're going to move that 160 over to the other side. And then we're going to square root both sides and find out that he needs to throw that balloon with a speed of 13 meters per second. I think it was like 12.6, but he should probably throw it with 13 if he wants to be sure his friend's going to be able to catch it. Hopefully all this work helped you out, and if you were unclear on some of these, you were able to figure out your problems. And I would recommend practicing these again on your own. It always looks easy when someone else does it for you. But if you practice again on your own with a blank piece of paper, it'll help build those skills so that you won't struggle as much with the math in this physics class. Good luck!